Good morning, respected members. I am Jada Nageshwara, research scholar from Department of EC, JND University. Today, I will briefly present my research work titled High Gain Slotted Rectangular Patch Antenna Loaded with Circular Split Ring Resonator. Which I, here, the motivation and problem statement of this research is the first motivation. The microchip patch antennas are widely used due to their low profile and low cost and easy of application. However, their major limitations are low gain and narrow bandwidth and poor directivity. These limitations make conventional patch antennas unsuitable for X-band applications where high gain and wide bandwidth are essential. Hence, the objective of this work is significantly enhance the gain and bandwidth of rectangular patch antenna while maintaining the compact size. Okay, now, for getting these objectives, I can consider from the literatures some techniques like DGS, defected ground structures, slots on patch antenna, and metamaterial inspired structures like SSR and CSR. Firstly, we see the abstract of this paper. This paper presents the design of circular splitting resonator loaded high gain slotted rectangular microchip edge antenna. The frequency notch characteristics. Already, I told the primary goal of this research is improve the traditional microchip antenna gain and bandwidth while it operates in X band. Then, whenever can consider the CSRR is acting as a metamaterial, deploying on the patch to get the desired characteristics. Okay. Then finally, the suggested antenna provides a gain of 21.1 dBi and 12.0 dBi at two different peaks as their pair radiation profile and resonate at a 10.76 gigahertz with S11 parameters of minus 18.94 dB. Okay, na? This is the abstract of this paper. Then how can get this objective from conventional microchip antenna? We will see here. You have some methodologies we should follow. Okay, follow. This is the proposed based on the literature survey. I told based on the literature survey, uh, I can improve the my objectives with help of some techniques like DGS and slots and the metamaterial inspiration. Then let's see. This is the proposed system of my research work. In this, I presented antenna features a rectangular shaped patch design incorporating the asymmetric plus slots, DGS, and the metamaterial. Let's see the dimensions of the presented square patch antenna are outlined table in the below. These are the dimensions of my patch antenna. Okay, na? Let's see here. If you observe here, this is the final proposed structure with the DGS and metamaterial inspiration and the asymmetrical plus shot. But how we can get this asymmetrical plus shot means based on the some techniques. For the first one, let's see the evolution of a proposed antenna. The first one here I can consider three evolutions. One is the conventional microchip patch antenna. The first of all, we design the conventional rectangular patch antenna with the standard equations as per our resonating frequency. These are the two equations we have for designing the conventional microchip patch antenna. Then we can get the our objectives based on these techniques. Like first one is slots. Then the impact of the impact of slots on rectangular patch antenna using the strip feed. We will see here. You can take the three types of slots on conventional microchip antenna. One is the square, other one is plus slot, other one is asymmetrical plus slot. Okay, now whenever you can comparing these all things, first of all, how to choose these slots on microchip antennas based on the electrical properties, where you have the better electrical current distribution. Then I can alter that electrical distribution. Based on that, I can get the resonances of S11 parameters. Let's say these are the three S11 parameters of three designs: symmetrical, rectangular, and asymmetrical. Okay, slots, among these three slots, okay, the asymmetrical slots give the better results. That's why I can choose this asymmetrical plus slot for further modification. Let's say these are the results of asymmetrical plus slot. Okay, then after getting this optimization design for slots, then go for the DGS. Then let's see how the effect of DGS on this uh, method. The DGS refers to a printed. The DGS refers to a printed. Let's see, these are the two structures I use for DGS. One is raised triangular DGS with a plat of in a rectangular microchip patch antenna as shown in the figure A. Other one is raised triangular DGS with a rectangular DGS offers a peak gain like 4.6 dBi at 10.55 GHz. Then next, you see these are the S11 parameters of these two types of DGS antennas. If you observe here, return loss of a rectangular patch antenna with the slots and DGS by varying the geometry. But the second geometry gives the better results than the first one. I mean, raised rectangular shape with a rectangular cut. Rectangular cut antenna gives the better results. The black S11 gives the second step. Then further, you didn't get our expectations as per our abstract. Then further we go for the third technique is metamaterial inspiration. Okay, now let's see how the effect of metamaterial with this rectangular microchip patch antenna. If you observe, this is the SRR unit cell, circular split ring resonator unit cell, and this is a double negative feature. Then I observe from the S11 and S21 parameters, and then with help of then some iterations I can observe the behavior of our microchip patch antenna. Let's see, this is S11 parameters. Here also same thing. With help of this metamaterial, we can improve the gain at most. Then let's see, this is the S11 parameters from iteration 1, iteration 2, iteration 3, and iteration 4. The first iteration is the metamaterial placed around the slot on patch. Then we will get this type of results. Then next we go for the clockwise direction, the placement of this splitting resonator, circular splitting resonator on a patch. Then here also I didn't get some expectations. Then go for the last iteration, fifth iteration around this one. Then let's see, this is the S11 parameters of a last iteration of that to fifth iteration. We have the wide band and two peaks. Then I can measure the gain at these two peaks. It gives the 21 point. These are the gain results: 21.1 dBi and 12.0 dBi at two different peaks. Then go to the results and discussion. You will get the better results than optimized microchip patch antenna. These are the E plane and H plane radiation patterns at these two resonant peaks. Again, if you observe the radiation patterns, these are a proper radiation patterns of these two peaks. From the radiation pattern, you can observe the how radiation distributes. I mean, radiation nothing but power distributions among the microchip patch antenna. Okay, now these are the results of this research work. Then let's see the performance table of our proposed antenna. The first one is rectangular microchip patch antenna with asymmetrical plus start. These are the resonant frequencies, and the bandwidth is 550 megahertz, and the gain at single resonant frequency is 11.7 dBi. Then go for the another modification of antenna, rectangular microchip patch antenna with asymmetrical plus and DGS structure. Here also we have the two resonant peaks. These are not resonant peaks. The radiating frequency from 9.0 to 10.89. Here get the bandwidth is 1870 megahertz, and the gain is 7.6 at one resonant frequency. Then whenever you can move to the iterations of CSRR, okay, na, we'll get the better bandwidth and the better gain. Better meaning with exceed the gain at two peaks, that is 21.1 dBi at 10.76 gigahertz and 12 dBi at 10.34 gigahertz. Okay, this is the performance of microchip patch antenna. This table compares the different antenna structures with their evolution. Then after conclusion, In this work, metamaterial loaded microstrip patch antenna is presented and its performance parameters are evaluated. It is demonstrated that adding fifth iteration of split ring resonator results in gains of 20.1 dBi and 12.0 dBi respectively at two peaks. It is noted that the patch provides a broader bandwidth. Therefore, the presented antenna with the 5 splitting resonator offers a great gain and bandwidth for expand applications. Okay, this is our objective. Then how we can reach this one means with the help of this flow, we can reach the this one. These are some references I have. From this reference only, I can finding the gap of my research work. Gap of my research work. Research work. Then, thank you all. Is there any questions?